Okay, so welcome to the Oxford Discrete Maths and Probability Seminar. It's a great pleasure this week to have Annika Heckel, who's going to talk on her work on the chromatic number of the random graph.
Yeah, so thank you for the invitation to speak here and for the introduction. So the chromatic number is a classical topic in graph theory. So suppose we want to give a color to every vertex so that neighbors get different colors. Then the chromatic number is the minimum number of colors where this is possible. Now, suppose we pick an n-vertex graph uniformly at random. So we take the set of all possible graphs on n-labeled vertices, we draw one at random, and we work out its chromatic number. And then we repeat this experiment. We pick another random n-vertex graph. Will it have the same chromatic number? Or if not, how far apart are the chromatic numbers of the two graphs likely to be? Now, the chromatic number of a uniform n-vertex graph is, of course, a random variable. So what we're asking is, well, how wide is the distribution of this random variable? So does this random variable behave essentially like a deterministic function, and the weight of the distribution is concentrated on only a few values which are close together, or is the distribution completely spread out between 1 and n? Now, until recently, we didn't know whether or not the distribution of this random variable is concentrated on constantly many values or not. And the main results that I'm going to talk about in this talk is that at least for infinitely many values n, the chromatic number of a random n-vertex graph is spread out over at least about root n values. Okay, so a random uniform n-vertex graph is a bit unwieldy, but luckily we've got a better way of generating this graph. So we can just look at g in 1/2, where we include every edge independently with probability 1/2. And of course, more generally, we can ask about the chromatic number of the random graph GNP. Results about the chromatic number of GNP generally falls into two categories. So the first question we can ask is, what is the typical value of the chromatic number of GNP? Can we prove upper and lower bounds that hold with high probability if n is large? And the other question is, okay, even if we know the typical value, or even if we don't know it exactly, can we say something about how much the chromatic number of GNP varies? Now, on the first question, the value of the chromatic number, there's the classic result by Bollobás from '87, who proved that the chromatic number of g in 1/2 is asymptotically given by this expression with high probability. So it was already known that this is a lower bound, and he proved the corresponding upper bound. Now, this was sharpened several times over the years and also generalized to GNP for all p, or almost all p. Now, the best bounds for the chromatic number of g in 1/2 at the moment are from 2016. So we have this expression here for the chromatic number, and it holds up to an error term of size n over log n squared. Now I'm writing out this formula because this result will become important later on when we talk about concentration. So you don't have to remember this formula, but maybe keep in mind that we have some expression that estimates the chromatic number that holds up to an error term. Now, how about concentration? Of course, this result is already a concentration type result. So we've specified an explicit interval of length little o of n over log n squared, which contains the chromatic number. So this already tells us that the chromatic number is spread out over at most n over log n squared consecutive values. But it turns out that if we don't have to specify the interval, we can do a lot better than this. So there's a very general result by Shamir and Spencer from '87. So they proved, using martingale concentration, that the chromatic number of GNP for any function p of n, so you can plug in any p of n that you like, And then there's a sequence of intervals of length about root n that contains the chromatic number with high probability. And this result, yeah, it does not give you any information whatsoever on what these intervals are, but we know they exist and the chromatic number is contained in them with high probability. In this general form, this result is optimal, which you can see if you, if you consider a very, very special case of P. So if you plug in P that tends to 1 at the correct rate, then kind of for silly reasons, you can see that the chromatic number in this case is actually spread out over about root n values. But that's just because in that case where we have kind of a full random graph with only a few edges missing, yeah, it comes from the variation in the number of edges, which is about root n. So this is not the most interesting example, but yeah, in this general case, in this general form, this result is optimal. Now, for special P, it can be improved considerably. So in particular, for our favorite P, P equals 1/2, we can gain a log factor, which was proved by Alon. But if P tends to 0 quickly enough, so in particular, if P is less than n to the -1/2 minus epsilon, in fact, the length of the interval can be reduced to 2. So there are 2 consecutive values in this case, so that the chromatic number takes one of these 2 values with high probability. So this was proved by Alon and Krivilevich in 97. So here, the chromatic number of GMP does actually behave, well, almost like a deterministic function. If you've sampled G and P and you've worked out the chromatic number, then with very high probability, you can predict the chromatic number of the next G and P, plus minus 1, say. So starting from the late 1980s, in view of these sharp results showing concentration of the chromatic number, Bollobás started asking the opposite question. So he asked, can we find any non-trivial examples where the chromatic number is not concentrated? And in particular, he focused on G and 1/2. And he asked, can we at least show that the chromatic number of G and 1/2 is not concentrated on, say, 100 consecutive values? Now, if you compare this to the upper bound that we have in this case, that's quite far away from this. So it does not seem like the most ambitious goal, but still this stayed open for quite some time. And I think the reason that it stayed open for quite some time is that we don't really have very many tools to prove non-concentration of a random variable. So we have a number of concentration inequalities that give us upper bounds, and maybe there are some special cases where we can work out the entire approximate distribution of a random variable, and that implies lower bounds in concentration. But there are few ways of just proving non-concentration without working out the entire distribution. So here, as promised, is the main result of this talk. So the result is that whenever we have a sequence of intervals, Sn Tn, that contains the chromatic number of G and 1/2 with high probability, then there are infinitely many n, so that the length of the interval is at least n to the 1/2 minus epsilon, where epsilon is an arbitrary constant. Or in fact, we could plug in little o1 here, which tends to 0 slowly. So if you compare this to the upper bound here by Alon, you can see up to this epsilon, this is optimal. So in 2019, I had this up to n to the 1/4, and now recently, together with Oliver, we've been able to get up to the correct constant. Okay, so I have two main goals for the rest of the talk. So the first is to kind of talk you through the method of how non-concentration is proved in this case without actually working out the entire distribution of the chromatic number. And how this method is applied in this case. And then secondly, I want to talk about what we think the correct concentration behavior of the chromatic number is, because I should warn you at this point, we do not think that this lower bound is true for every n. So we only show there are infinitely many n so that this holds. And in fact, we do not think this holds for every n. So I will say something about this at the end of the talk. Okay, so let's start with the method. So we need to prove non-concentration, we need two ingredients. So the first ingredient is actually we need a weak concentration type result. So we need some well-behaved function f of n, and a result that says the chromatic number is close to this function up to some error term with high probability. And we need a lower bound for this function. Now, don't worry what alpha and delta are, I'm going to say in a minute. So we need that a lower bound for the slope of the estimate, at least 1 over alpha for some function alpha, which I'm going to specify in a couple of slides, plus some, little bit of margin delta. The second ingredient is a coupling result. So we need a coupling. Essentially, we need a coupling of gn 1/2 and gn prime 1/2, so that their chromatic numbers are close together. More specifically, if we let n prime be n plus alpha r, alpha is the function from above, we want, with at least, well, some sufficient probability, I've written a quarter here, the chromatic number increases by at most r if we increase n by alpha times r. Now, I'm also not telling you yet what r is, but we want r to be as large as possible to get a good lower bound on the concentration. Okay, what does the coupling do? The coupling tells us that if we have a sequence of intervals that contains the chromatic number with high probability, then the intervals are reasonably close together. So if up here, if we let n prime be n plus alpha r, then the coupling tells us that the intervals, the difference between the intervals is at most r, because with high probability, the chromatic number of gn 1/2 is in here, the chromatic number of gn prime 1/2 is in here, and also with probability at least a quarter, say, they are at most r apart. So the difference here can be at most r. So how do we put these two ingredients together to show non-concentration? So that's best seen in a picture. So the weak concentration type result is shown in this blue band. So we've got a function f of n. It has a slope which is bigger than 1 over alpha. And the chromatic number is, with high probability, somewhere within this blue band. So f of n plus some error term, plus minus some error term, delta of n. And the coupling, well, suppose we have some intervals, s and t, that contain the chromatic number. Then we know the slope between the intervals is at most 1 over alpha, because if we increase n by alpha times r, the interval moves up by at most r. Okay, so these red lines have slope at most 1 over alpha. And now if all intervals were short, then eventually this would lead to a contradiction, because as we increase n, here we go up with slope bigger than 1 over alpha. And here, between the intervals, we go up by at most 1 over alpha. And if we don't move up enough within the intervals, eventually we would get an interval like this one that's outside the blue band. Okay, so close to every n, there must be at least one long interval. And if you work out all the numbers, you get an interval of length roughly alpha delta r. Now alpha will be more or less given, it will be about log n, delta will be about 1 over log squared n. So overall this alpha delta is 1 over log n. So we need r to be as big as possible to get a long interval. Okay, so at this point I should finally tell you what alpha of n is. So I've kind of suggestively named this alpha of n because it's the independence number of gn 1/2. So the independence number of a graph G is just the size of the largest independent vertex set, so the largest vertex set without any edges between them. And in Gn1/2, the independence number is it's really easy. There's some deterministic function, which I'm also calling alpha of n. I'm not writing out the whole function here, but it's roughly of logarithmic size. And we know for almost all n, with high probability, the independence number of Gn1/2 is exactly this function alpha of n. So this is a result from the 70s proved by Matula and also by Bollobás and Erdős. Okay, so this is alpha of n. Now, why would you be looking at the independence number if you were thinking about the chromatic number? In every graph, you get a lower bound for the chromatic number, which is n over the independence number. And that's because, by definition, in a coloring, because neighboring vertices get different colors, every color class, so all the vertices of one particular color, is an independent set. So every color class has at most alpha of g vertices in it. And so if there are n vertices, the chromatic number has to be at least n over alpha. So that's true in every graph. But in Gn1/2, or more generally in GMP, this lower bound is asymptotically correct. And in fact, so the formula we had on the second slide or so shows that the chromatic number of Gn1/2 is given by n over alpha minus some constant. The constant is something like 3 or 4. So this means that we can color Gn1/2 so that the average color class size is just a constant from this maximum size that any color class can possibly be. So yeah, so we're coloring Gn1/2 on average with very large independent sets. And the intuition is now, well, an optimal coloring of Gn1/2 probably contains all or almost all independent alpha sets as color classes. So I could go into this in more detail. So we think the chromatic number of Gn1/2 is close to the point where the expected number of colorings is at least 1. So the smallest k, so that the expected number of k colorings is at least 1, more or less. Well, if you condition on the number of alpha sets, then it turns out you want to take as many of those into your coloring as possible to maximize the expectation. Okay, but anyway, so it seems plausible that the optimal coloring contains most of the maximum independent sets. And that kind of suggests that the chromatic number of Gn1/2 should vary at least as much as the number of available sets of size alpha, which I'm going to call x alpha. So x alpha is the number of independent sets of maximum size. And we don't only know what the independence number is almost exactly, we also know what the distribution of the number of maximum independent sets is. So you can use Stein's method to show that this is roughly Poisson distributed. Well, I'm going to say what mu is in a bit. But this means that, well, the number of independent alpha sets is not too tightly concentrated. It varies by about root mu. And so the chromatic number should also vary more or less like root of mu. And mu, you can write this as n to the rho, where rho is a function that's somewhere between 0 and 1. And depending on n, it's sometimes close to 0 and it's sometimes close to n. So if we pick an n so that this rho is close to 1, then the variation in the number of alpha sets is almost n, almost root n. And then in this case, it kind of seems plausible that the chromatic number should also vary by something close to this. Okay, so this is kind of hand wavy, but that's the intuition and why we're looking at these alpha sets. Okay, so let's see how we get the two ingredients that we talked about for this alpha. Okay, so first the weak concentration type result. So we wanted some estimate for the chromatic number f of n, some function plus minus an error term, so that the slope df over dn is bigger than 1 over alpha. Now, luckily, we already have this. So this is the estimate from the second slide. So if we use this estimate, so this is now f of n, and this error term is delta, and we take the derivative, then we actually get this. So df over dn is at least 1 over alpha plus something of order 1 over log n squared, unless mu alpha is very close to n. So we can't go all the way up to n with this. I'm also going to say something about this later, so how close we can actually get to root n. But yeah, so so luckily we don't have to do any work here. We've already got this result here, and it's actually quite lucky that we do, because the best estimate that existed before this result wouldn't have worked in this proof. So we really do need this. Okay, so how about the second ingredient, the coupling? So we want a coupling of gn1/2 and gn prime 1/2, so that, well, if we increase n by alpha times r, with sufficiently high probability, the chromatic number increases by at most r. And we want r to be as large as possible, preferably to get a good lower bound on the concentration. Okay, so how do we construct this coloring? This coupling. So we do kind of something that seems really obvious. So the difference in the number of vertices is alpha times r. So let's pick r vertex sets of size alpha randomly, make them independent sets, so we don't put any edges into these sets. And then every other edge, so everything that's not within these r random sets of size alpha, we include with probability 1/2 independently. Okay, so what does this construction do? So here inside this graph that we call G is just a normal gn1/2. So that's good. It's also clear if we call the outer graph G prime, then the outer graph, the chromatic number of that, is at most the chromatic number of the inner graph plus r, because, well, all of these vertex sets are independent, there are r of them, so we can give each of them their own color. And that way we can extend any coloring here of the inner random graph to a coloring of the whole graph using r more colors. Okay, so that's also good. Now, the problem is G prime is not gn prime 1/2, because we've planted these r random alpha sets. So we've disturbed the distribution of gn prime 1/2 with that. So what's left to do is to show that the outer random graph is similar enough to a gn prime 1/2, at least as long as r is not too big. We want r to be as big as possible. Yeah. So how do we do that? So it's actually cleaner to do this by studying the effect of planting just one alpha set, one independent set of size alpha. Let's call this the planted model. So the planted model is like what we did before, but now we just we pick one vertex set of size alpha, we make it an independent set, and everything else, every other edge is there independently with probability 1/2. Then the key lemma is that if we do this, plant one alpha set, the total variation distance between gn1/2 and this planted model is of order 1 over root mu, where mu is the expected number of alpha sets. Now, if you don't know what the total variation distance is, then don't worry, I have a definition on the next slide. But what this means is that we can couple gn1/2 and the planted model so that they are exactly the same with probability at least 1 minus order 1 over root mu. Okay, so and actually the proof of this key lemma is quite short. It fits on this slide. How do we prove this? So the total variation distance of well, if we have discrete random variables, we can write it like this. So it's 1/2 times, well, the sum every value the random variable can take. In this case, the random variable is the graph. So we take the sum over all graphs on n vertices. Confusingly, I've called this G, so this is not the same G as in the coupling. So this is a sum over all graphs on n vertices. And we subtract the probability that the planted model takes the value G, so comes out as our given graph G, and the probability that the normal G in 1/2 comes out as G. And these probabilities we can actually write out exactly. So let's start with this one. So this is just 1/2 to the n choose 2. Okay, this was easy. How about this one? So what has to happen for the planted model to come out as a given graph G? Well, first of all, the planted alpha set has to be one of the sets, independent alpha sets in G. So there's X alpha of G of them. And this is 1 over n choose alpha is the probability that we pick this particular alpha set. And then all the remaining vertices, all the remaining edges, of which there are n choose 2 minus alpha choose 2, have to come out correctly, so either present or not present. So that's this term. Okay, and yeah, that's it. So now let's rearrange the terms. I want to pull out 1/2 to the n choose 2 here, and then here we're left with X alpha of G minus, this is mu, the expected number of alpha sets, and here this is also mu. So we come out at exactly 1/2 times the expected absolute deviation of X alpha from its mean over its mean. Okay, and this, well, we know X alpha is Poisson distributed with mean mu, so this is actually of order root mu, but we don't need the Poisson distribution. We actually can just use an upper bound on the variance. So we only need that the variance is of order mu, and then this whole term is of order 1 over root mu. Okay, so this is the whole proof of the key lemma. I wanted to have one proof in here. But yeah, if you didn't follow, just know we've now proved the key lemma. And hopefully now it's plausible that if we can kind of glue together these couplings or repeat this step r times, so that, if we use at most little o of root mu alpha sets, so if we plant little o of root mu of them, then the total variation distance between this planted model here, this G prime, and the normal G n prime 1/2 is little o1. Okay, and this also makes kind of sense on an intuitive level, right? So root mu is kind of the natural variation of X alpha. So if we plant little o of the variations you have anyway in these counts, then the random graph doesn't really notice that we've put in these extra alpha sets. The distribution is still more or less the same. Okay. Yes, so overall, now this whole thing gives us a coupling of this normal G n 1/2 with this G prime, and then of G prime with G n prime 1/2, G prime with G n prime 1/2, so that the chromatic number goes up by at most r. Okay. Yes, so this is how you get the coupling. And I think that's all I wanted to say about the proof of this theorem. Now, as promised, let's talk a little bit about what we think the correct concentration behavior is for all n, because we don't think it's root n or close to root n for every n. Now, if you recall, the number of alpha sets, which we called X alpha, is roughly Poisson distributed with some mean n to the row, which is between n to the 0 and close to n to the 1. Now, if you plot this function rho, it looks like this. So, well, let's look at one of these lines. So here you start out with about, well, say 1 alpha set, and then as you increase n, the expected number of alpha sets increases more and more and more until you're close to n alpha sets. And then at this point, alpha plus 1 sets start appearing. So here the alpha changes to the next integer, and we start out with about 1 alpha set again. So if you stick with 1 set vertex set size, then this continues as a straight line up here. So the discontinuity comes from changing to the next integer. Okay, and so the expected number of alpha sets varies by plus minus root of that, so between n to the 0 and n to the 1/2. So a reasonable conjecture is that the chromatic number is not concentrated on fewer than about this many values. So this log n comes from, well, this estimate for the chromatic number. It increases by, well, sufficiently more than 1/alpha, and the sufficiently more makes this 1/log n. So 1 alpha set, an extra alpha set gives you about a benefit for the chromatic number of 1/log n. Okay, so this is the finer conjecture that we had, and in the theorem before, I didn't explicitly say that. We look at the case where we are here, where we are very close to n to the 1 or n to the 1/2 here. But of course here, we have a different lower bound. Now, if we look at the proof in more detail, we actually get the following better result. So actually what we show is that at least if we're not at these top points, so if rho of n is less than, say, 0.99, then for every n, there's some n star nearby, so that essentially this conjecture holds. So yeah, so we have some constant here. Yeah, so we still don't show anything for any particular n, but at least we show that for every n, there's an n star nearby, so that this conjectured lower bound holds for the interval length. Right. Okay, so that's one lower bound that we have for the concentration and one conjecture. So from now on, I'm not going to bother very much with the log terms. So I've put this, whenever you read little o1, it's some log factor. Okay, so we have this conjectured lower bound. What other possible sources of variation in the chromatic number are there? So if p tends to 1 at the right rate, then the number of edges kind of induced considerable variation. This does not seem to be the case for g in 1/2. So for p constant, we can couple g and p and g and m where we fix the number of edges so that their chromatic numbers only differ by about order log n. So the number of edges can't make more of a variation than something of order log n. So that does not seem to be an important source of variation. Now, what does seem to matter is the number of alpha minus 1 sets. So the number of alpha minus 1 sets is still roughly Poisson. But the expectation is slightly larger. The expectation is now about 1 plus rho times some log factor. So this varies by about n to the 1 plus rho over 2. And now if you look at the heuristic again, that the chromatic number is close to the point where the expected number of colorings is roughly 1, or that at least it varies like the point where the expected number of colorings is close to 1. And you condition on the number of alpha minus 1 sets, then if you decrease x alpha minus 1 by a typical amount, then you need to increase the number of colors by about n to the 1 minus rho over 2 times some log factors to still make the expected number of colorings come out as 1. So this should be, well, we conjecture that this is another lower bound for for the variation in the number of colors that we need for the chromatic number. Okay, so we have these two sources of non-concentration. Are there any others? So can we continue maybe with the alpha minus 2 sets and alpha minus 3 sets? Maybe they all give us some non-concentration. But that does not appear to be the case. So there's a paper I'm currently writing up together with Kostas Panagiotou. So in the paper, we show that if you ban alpha and alpha minus 1 sets, and you look at something called the alpha minus 2 bounded chromatic number. So that just means it's like the normal chromatic number, except we don't allow any color classes bigger than alpha minus 2. Then this is actually very sharply concentrated. So by a very complicated application of the second moment method, we can show that this takes one of at most 2 consecutive values with high probability. And that's despite this being actually fairly close to the normal chromatic number. So for the alpha minus 2 bounded chromatic number, for example, we have the same estimate that you saw on the second slide. And still, this seems to be very narrowly concentrated. Well, yeah. So the conjecture, which arose from the work of several people in recent years, which we call the Zigzag Conjecture, is that in fact these lower bounds coming from the alpha and alpha minus 1 sets are essentially the truth up to lower order variations. So we have a lower bound coming from the number of alpha sets, which kind of goes up like this from 0 to 1/2. So here I'm plotting, so if we're here, then this lower bound is n to the 1/2. There's the lower bound coming from the alpha minus 1 sets, which kind of goes the other way. And they actually go like this in straight lines if you plot this on a log scale. And now the conjecture is that this red line, this red zigzag line, up to lower order terms is actually the concentration of the chromatic number. Now we also make a number of finer conjectures in the paper. So in particular, so here, if you look at one of these spikes, so this line going up and going down, so here the number of alpha sets is the dominating source of non-concentration. And here it's the alpha minus 1 sets, but actually that's the same number because here the independence number increases. So during one of these spikes, we conjecture that essentially, if you know how many independent sets of this size you have, up to lower order variations, you can predict the chromatic number. And this also implies a Gaussian limiting distribution for the chromatic number here. We also thought about what happens in the best case and in the worst case, so kind of at where these lines intersect. So in the best case, the concentration, we think it's n to the 1/4 over log to the 7/4. So this is maybe a weird log factor here. This is just, so there's not much to this. This is just where these lines intersect if you work out what the exact log factors of the lines are. Now the top is a lot more interesting. So we think in the worst case, the concentration is root n log n over log n cubed. And this is not just where these lines intersect. So here, and this happens when the expected number of alpha sets is n over log n squared. So this is, well, here, how much the chromatic number varies, we think that's the variation in the number of alpha sets times the benefit that each alpha set gives you. And most of the time, this benefit here is 1 over log n. But as you get close to this point, this benefit actually decreases. So the variation in the number of alpha sets increases as you go up here, but the benefit per alpha set decreases. So you've got a product of an increasing and a decreasing function. And up here, somewhere this maximum is reached, and then it goes down again. And well, it actually takes quite a lot of work to work out how exactly this this benefit per alpha set changes as you go up here, but we think it's maximized at mu alpha equals n over log n squared, and that the worst case n, so this maximum here, is of this size. Right. Now, how close can we actually get to the upper bounds or to this maximum? So as things currently stand, the best result is n to the 1/2 minus little o1 for some unspecified function little o1. And the bottleneck here is the error term little o of n over log n squared from our explicit estimate that we used as our first ingredient. Now, in the upcoming paper with Kostas Panagiotou, we also plan to prove a sharper explicit estimate for the chromatic number of G in 1/2. And given this sharper explicit estimate, if we use that as our first ingredient in the method, actually the lower bound for some n can be improved to some constant times what we think is the optimum. So yeah, assuming the sharper explicit estimate, the method gives what we think is an optimal result. I've got plenty of time, but somehow I've already reached the last slide. So let's talk a bit about open questions. So the biggest open question, obviously, is, can we verify this zigzag conjecture? So does the correct concentration interval length zigzag between n to the 1/4 times some log factors and n to the 1/2? Now, short of that, now the whole method that we use to give a lower bound on the concentration, it never gives anything for any particular n. We don't know for which n's the chromatic number is not concentrated. Of course, we think it's for every n, but we don't prove this. So another nice thing would be to prove anything whatsoever for every n. Now, at the top of the zigzag, our conditional lower bound is root n log n over log n cubed. The upper bound due to Alon is root n over log n. So it would be nice to close this gap and preferably give an upper bound that matches this one. And finally, how about other ranges of p? So I've only talked about p equals 1/2 here. Now, many of these things, almost all of them, or at least the root n minus epsilon result, n to the 1/2 minus epsilon results, holds for every p, and we've proved it for every constant p, and we've proved it for every constant p. Now the zigzag conjecture, we're not sure whether that holds for every constant p. Well, we're not sure it holds at all, but we don't conjecture it for every constant p, because the chromatic number, the behavior kind of changes if for p bigger than about 0.886. But even more interestingly, what happens if we let p tend to 0? So we know coming from below, for p less than n to the minus 1/2, we have 2-point concentration. Coming from above, we have non-concentration for constant p. Well, where do these two things meet? How far down does non-concentration go? Yes, and that's the end of the talk.
Great, thank you very much, Annika, for a fantastic talk. It's lovely results. So we can have some questions. So if anyone has questions, please feel free to signal in the chat or with a hand or to unmute yourself. Actually, maybe first I could ask, so a couple of questions. So you were saying that you don't believe the zigzag conjecture for all constant p. Do you believe it for all constant p less than
1 minus 1 over e squared? Yes. Okay. Yes, I think, yeah, I believe it for p less than 1 minus 1 over e squared, and above that, I'm not so sure what's going on.
Okay, and the so the lower bound of n to the 1/2 plus little o1. I know you don't have it pinned down exactly where you have it. How I mean, do you have it reasonably approximately, or is it?
Sorry, I didn't catch the question.
How much do you know about locations where you actually get the lower bound of about root n? I mean, is it nothing at all? You know, it's approximately where you expect.
Well, yeah, we know it's within multiplicative 1 plus little o 1 of every n that's kind of close to where it's supposed to be. So you start with n where you think it's true, and then you find an n star within 1 plus little o 1 of that.
Okay, yeah, okay. Actually, you did say that already, yeah. Thank you. James, I think, had a question.
I can ask something. I'm quite curious to hear what happens when p is bigger than that threshold, 0.86. Is that complicated to explain?
Well, yeah, it is. Yeah, a little bit complicated to explain. Yeah, so we get to a point where the average color class size in a coloring is actually very, very close to alpha, and then kind of strange things start happening. So yeah, we can't, at this point, we can't actually realize the average color class size, which is close to the point where the expected number of colorings first starts tending to 1. Because that point is so close to the number of alpha sets that we don't have enough sets of size alpha and alpha minus 1 to kind of make it happen to come out at this average color class size. Yeah, it's kind of hard to explain this without actually drawing anything.
So below that threshold, I mean, what's the picture of how much these independent alpha sets overlap? Do they overlap? I mean, the typical one doesn't overlap with any of the others. Is that true? But some of them.
No. So here, if you have less than root n alpha sets, then they, with high probability, they don't overlap. And then here, some of them overlap. So some of them overlap in one vertex, but typically not more of them. More than that, and only a few of them. So yes, here you can't actually take all of your alpha sets into your coloring because some of them overlap, but it's only a small fraction of them.
I see. So a typical one wouldn't overlap potentially.
Yes.
Okay.
Isn't this n over log n squared exactly the point where a typical one starts to overlap with?
Possibly, yes.
I've forgotten.
Might be.
I think so.
Mm-hmm.
Actually, I had another question, which is, can you say a little bit more about why GNM and GNP are so similar? that was a bit of a surprise to me, at least.
Really, because you gave me this argument like 2 years ago.
it's my memory is short.
Okay, I also don't remember, but it's in one of my papers. Let me see. Okay, so you start with GMP and you kind of sprinkle some edges to come out at a particular GNM. Okay, so you want a particular GNM. You start with GMP with P slightly smaller, and you sprinkle some more edges to come out at the correct number of edges. And you can show that if you start with some coloring, then not too many color classes are messed up by these few edges.
Thank you. Any other questions? Okay, well, let me say thank you to Annika again for a fantastic talk, which I very much enjoyed. And let me invite everyone to unmute